Okay, another way that I can multiply two vectors together is through the dot product, also known as the scalar product. And the reason for that is because when I dot two vectors together, the result is actually a scalar, as opposed to the cross product where the result was another vector. This time I only get a magnitude or just a scalar. And by definition, if I have two vectors, say A and B, separated by some angle theta, the dot product, the scalar product, is just the magnitude of A times the magnitude of B times the cosine of the angle between them, as opposed to the sine of the angle with the cross product. So it's opposite there, as well as the fact that this is a scalar, not a vector. It has no direction, just a magnitude. So when doing this for Cartesian vectors, if I look at unit vectors and I dot I with I, okay, they each have a magnitude of 1, and then the angle between them is 0 if they're laying right on top of one another. So cosine of 0 is of course 1. So the result of I dot I equals 1. Okay, conversely, if I take two different vectors, this works for I dot j, j dot k, I dot k, doesn't matter. It's still going to be magnitude 1, and then cosine 90, because the angle between any other two vectors, unit vectors, is going to be 90. Now the cosine of 90 is of course 0. Okay, so again, this is opposite from what we had with the cross product, because again we're dealing with cosine instead of sine here, right? I cross I equals 0. Here I dot I equals 1. Okay, so when I plug that into an equation, right, I've got ax, ay, az, ab, bx, by, bz. Okay, I'm going to take this term times this term, and then I dot j, I dot k, do the same thing with j dot k, blah, blah, blah. Everything drops off, okay, all the unlike terms, so I dot j, j dot k, so on and so forth, they go away. All I'm left with is the like terms, which is ax, I dot bxi, ayj dot byj, and azk dot bzk. And really all I'm left with is axbx plus ayby plus azbz. So it's essentially multiplying the like terms and summing them up. That's how I do a dot product. And again, remember that I just get a scalar magnitude quantity when doing this. Okay, so why do I care about this? Okay, well, the first application is to find an angle between the two vectors, which is very easy in 2 dimensions, right? We can just use geometry and trigonometry to figure out the angle between two vectors. But in 3 dimensions, that's next to impossible. So if I have two Cartesian vectors, and these can be any two Cartesian vectors, it could be position vectors, force vectors, unit vectors, or any combination thereof. Okay, and just rearranging my definition and solving for the angle, I can find the angle knowing my two vectors that I have. And I can find the angle between them just by taking the dot product of the two vectors divided by the product of the magnitude of the two vectors, taking an inverse cosine of that. Okay, so that's one application of the dot product, is to find an angle between two vectors. The second one is to find basically the magnitude of a vector in a specific direction. Okay, so for example, if I've got this A vector and I want to figure out how much of that A vector is going in the lowercase a axis. Okay, well, in 2 dimensions, again, this is pretty easy. I just know it's going to be, the magnitude of this side is going to be nothing more than a cosine theta, right? Because it's adjacent to the angle, okay, a cosine theta. Okay, so finding that magnitude along the a-axis, again, it's just a cosine theta. I throw in this 1 here, okay, doesn't change the value. That's essentially the magnitude of a unit vector. So I can find the magnitude of a vector in a specific direction by taking that vector and dotting it with the unit vector in the direction which I'm interested in. So I can say, if I know A, I can find the unit vector u sub A, dot those two together, and find the magnitude of A in the lowercase a direction. Okay, so I can do that with a force, or I can do it with a moment like I have here. Same general idea. I just take the magnitude or the vector of my moment and I dot it with the unit vector that I'm interested in, right? The direction I'm interested in. Okay, so if I take, for example, this, I've got the AA axis going vertically here. I put some sort of force on it at some point, A. I can find the moment, okay, the total moment about point O, which actually is along this B axis. And I can simply project that over onto the A axis by doing that dot product. And this becomes very important in a moment type situation, because oftentimes I'm putting a moment on something, but I'm really only concerned about the component of the moment, say around the angle of twist, right? If I've got bearings here, okay, I'm not always putting a perfect moment on them. I need to know the component of that moment in a certain direction. And I can do that by taking the total moment and dotting it with the unit vector in the direction that I'm interested in finding the component of its magnitude.